So the final thing in the binomial theorem chapter is doing binomial expansions with partial fractions. So this is where we want to find the binomial expansion of something that can be written in partial fractions. So writing in partial fractions isn't the only way to expand something like this as an infinite series, but it's probably the easiest way. Because, of course, a different way we could find the expansion of this is by multiplying together the three series, or these two things here you can expand using the binomial theorem, and then we could multiply by 4 minus 5x. This is horrible. So do not do this, because this is not a very sensible way to work out or to find the binomial expansion of this. A much better way would be to write this in partial fractions. So we need to write it as something over 1 plus x plus something else over 2 minus x, where a and b are constants we need to find. So if we multiply everything through by the denominator, we get 4 minus 5x equals a times 2 minus x plus b times 1 plus x. And then we need to find a and b. So to find to find b, we could let x be 2. And then we're going to get 4 minus 10, that's minus 6, equals a times 0 plus b times 3, which implies that b is minus 2. And to find a, we could let x be minus 1. And then we get 4 plus 5, that's 9, equals a times 3. So a is 3. And now we've written it in partial fractions. We've got 4 minus 5x over 1 plus x, 2 minus x, is 3 over 1 plus x minus 2 over 2 minus x. So now we can use the binomial theorem to do something with these two fractions. We can write this as 3 lots of 1 plus x to the minus 1 minus 2 lots of 2 minus x to the minus 1. And then these two things here we can expand using the binomial theorem. So let's do them separately and then put them back in a minute. So 1 plus x to the minus 1, that's 1, and then the next term is nx, where n is minus 1, so that's minus x. And then the next term is n minus 1 over 2 times x squared. And then the cubic term is n minus 1, n minus 2, over 3 factorial x cubed. And we don't need to go any further than that. So we've got 1 minus x plus x squared minus x cubed. And now we'll do 2 minus x to the minus 1. We have to be careful this time because we've got a 2. So the first thing we need to do is take the 2 outside. So we're going to have 2 to the minus 1 times 1 minus a half x to the minus 1. And now in the binomial theorem, everywhere in place of x, we're going to replace it with minus x over 2. So 2 to the minus 1, that's a half. And then 1, and then the next term is plus n times minus x over 2. So that's going to be minus 1 times minus x over 2. And then we've got n minus 1 times n minus 1 over 2 times minus x over 2 all squared. And then the cubic term is minus 1 minus 2 minus 3 over 3 factorial times minus x over 2 cubed. And then let's expand out everything. So this is a half. We'll leave the half outside actually, but inside we've got 1 plus a half x plus x squared over 4 plus x cubed over 8. Okay, and now we're going to replace this with the series we found here. And we're going to replace the other one with the series we've got here. Okay, so we're going to get 4 minus 5x over 1 plus x, 2 minus x is 3 lots of this red box. So that's 3 lots of 1 minus x plus x squared minus x cubed. And then minus 2 times the green box, a half times 1 plus x over 2 plus x squared over 4 plus x cubed over 8, and so on. And now let's expand this out. Notice the 2 and the half conveniently cancel out, so that's quite nice. That's why I didn't expand this out in the green box. So we've got 3 minus 3x plus 3x squared minus 3x cubed, and so on, minus 1 minus x over 2 minus x squared over 4 minus x cubed over 8, and so on. And this gives us 2. Then minus 3 minus a half is minus 7 over 2. 3 minus a quarter is 11 quarters. And minus 3 minus an eighth is minus 25 eighths. So this is the answer. And hopefully this agrees with what we're asked to show in the question, which we can see it does. And then the second part is to state the range of values of x for which the expansion is valid. So in order for all of this to be valid, we need these two expansions we did using the binomial theorem to be valid. So the top one, this one, we used x. So this is valid when the modulus of x is less than 1. And the one in the green box is valid when, well, we used minus x over 2 in place of x everywhere. So it's valid when the modulus of minus x over 2 is less than 1, which is the same as when the modulus of x is less than 2. So we need both of these two conditions to hold. We need both this and this. Well, that only happens when the modulus of x is less than 1. Because if the modulus of x was, say, 1.5, this first red box wouldn't be valid. This expansion would not be valid if x is anything larger than 1. So in order for everything to be valid, we need the modulus of x to be less than 1.